October 2025. While the world was obsessed with AI models getting bigger, with chips getting smaller, with Moore's Law dying, a team of Chinese researchers just published something in Nature that nobody saw coming. A memory chip built from materials that are literally one atom thick. Not a lab experiment, not a prototype that works once under perfect conditions. A fully functional flash memory chip, 94% manufacturing yield, mass production ready. And if you understand what this means, you'll realize the entire semiconductor industry just shifted on its axis. This is the memory breakthrough that could end silicon's 40-year reign. To understand why this matters, we need to talk about the crisis that's been quietly strangling the tech industry for years. It's called the memory wall. Right now, every phone in your pocket, every laptop on your desk, every data center training ChatGPT, they all depend on something called NAND flash memory. Think of it like a city made of skyscrapers. To add more storage, engineers stopped building out and started building up, stacking layers of memory cells. Samsung's latest chips, 232 layers tall. But this vertical city has a massive traffic problem. The electrons that move your data, they're stuck in increasingly congested elevators. The higher you build, the longer they wait. In tech, this is called the memory bottleneck. Your processor is a lightning-fast chef, but it's constantly waiting on the pantry. The memory to deliver ingredients, and it's getting worse. High-resolution video, massive open-world games, and especially artificial intelligence. They're demanding data at rates we can barely handle. GPT-4 has hundreds of billions of parameters. Everyone needs to be stored, accessed, moved around in the blink of an eye. The AI revolution isn't being limited by processing power anymore. It's being choked by memory speed. But there's an even bigger problem. Engineers have been fighting a losing battle against physics, shrinking memory cells down to just a few nanometers. At this scale, the weird laws of quantum mechanics take over. Electrons start doing something called quantum tunneling, literally passing through solid barriers like ghosts. For a memory chip that needs to trap electrons to store data? This is catastrophic. Data corruption, shortened lifespans, reliability nightmares. We've hit the physical limit of what silicon can do. The cost of squeezing out just a few more percentage points of performance? Tens of billions of dollars for a single fabrication plant. The industry has been desperately searching for what comes next. For years, the answer was purely theoretical, until October 2025. What the team at Fudan University just announced isn't an improvement on silicon. It's not even competing with silicon. It's the blueprint for what comes after silicon. And the clock to mass production? 3 to 5 years. Stay with me, because what they built is almost impossible to believe. In October 2025, in the journal Nature, one of the most prestigious scientific publications on Earth, a team led by Liu Chunsen and Zhou Peng at Fudan University unveiled their answer. They call it the CY01 chip, the changing architecture. This is the world's first fully functional two-dimensional NOR flash memory chip, integrated directly onto standard silicon using a process they call ATOM2CHIP, ATOM2CHIP. Let me break down what makes this so revolutionary. Two-dimensional materials are substances that are literally one atom thick, the thinnest materials physically possible. You've probably heard of the most famous one, graphene, a single layer of carbon atoms, stronger than steel, more conductive than copper. The Fudan team used a different material, molybdenum disulfide, a type of transition metal dichalcogenide. And here's why this matters. Electrons can zip through these 2D layers with almost no resistance. Data flows at incredible speeds, using almost no energy. But there's always been a massive problem. Working with a material one atom thick is, as you can imagine, incredibly difficult. Experts have compared it to carving a sculpture from tofu. It's fragile, it tears, it falls apart. The surface of even the smoothest silicon chip, while it looks perfectly flat to us, is rugged, mountainous terrain at the atomic scale. Placing a delicate, atom-thin sheet onto this surface would be like laying a silk thread over a gravel road, and then driving a truck over it. The material tears. Its electrical properties are destroyed. The chip fails. This challenge has kept 2D electronics trapped in research labs for over a decade. This is where the Fudan team's genius comes in. They didn't try to make silicon smoother. They didn't try to make 2D materials stronger. They developed a completely new integration approach. First, they used 2D materials that are inherently flexible, like using silk instead of glass. Second, they pioneered what they call modular integration. Instead of building everything at once, they fabricate the silicon CMOS circuits, the chip's brain, and the 2D memory circuits separately. The 2D layer is built on its own pristine surface. Then, in a highly controlled process, it's transferred onto the finished silicon wafer. Third, the critical breakthrough, high-density monolithic interconnection. They create millions of microscopic vertical bridges, bonding the silicon and 2D layers together at the atomic level. This isn't just stacking chips on top of each other. This is true three-dimensional fusion. The process includes a special conformal adhesion technique that allows the 2D material to flow over the microscopic bumps of the silicon surface without breaking, like pouring liquid over rough terrain. It fills every valley, covers every peak, creates a perfect, stable bond. And the results? The CY01 chip demonstrates a memory cell yield of 94.34%. Let me repeat that. 94% yield. That's nearly identical to commercial silicon production. This proves the process is stable, reproducible, manufacturable at scale. It supports full-featured 8-bit instruction operations and 32-bit high-speed parallel operations with random access. It's not a toy, it's a real, programmable, fully functional memory system. The operational speed, up to 5 MHz in testing, programming and erasing speeds, 20 nanoseconds, energy consumption per bit, just 0.644 picojoules, far below today's silicon flash cells. Data retention, 10 years, endurance, over 100,000 write cycles. This isn't a science project anymore, this is production-ready technology. But here's what almost nobody in the tech press is talking about. This breakthrough didn't happen overnight. The same Fudan team, just 6 months earlier, in April 2025, published another paper in Nature. They built something called the PoX Device, and it achieved a programming speed that shattered every record in semiconductor history. 400 picoseconds. Let me put that in perspective. 400 picoseconds is 400 trillionths of a second. That's not just faster than current flash memory. That's faster than anything ever demonstrated in a semiconductor charge storage device. Ever. In the entire history of computing. To understand how insane this is, current NAND flash takes microseconds to write data. That's thousands of times slower. Even the fastest SRAM, static random access memory, the memory in your processor's cache, operates in nanoseconds. The PoX device operates in picoseconds. This is the underlying technology that powers the CY01 chip. And here's why it matters for artificial intelligence. AI doesn't just need faster processors, it needs faster memory. Right now, the biggest bottleneck in AI systems isn't compute power. NVIDIA's H100 GPUs are phenomenally powerful. Google's TPUs can perform trillions of operations per second. The bottleneck is memory bandwidth, how fast you can move data in and out of storage. When you're training a large language model like GPT-4 or Claude, you're not just doing math, you're constantly loading massive datasets from storage, moving billions of parameters between memory layers, shuffling training data in and out of active memory. And you're doing it with NAND flash storage that was designed in the 1980s. Technology that takes microseconds to access data. When your processor operates in nanoseconds, it's like having a Formula One race car, but fueling it through a garden hose. That's why training cutting-edge AI models takes weeks or months. That's why it costs tens of millions of dollars. That's why data centers running AI workloads consume gigawatts of power. Most of that energy is wasted just moving data around. waiting for slow memory to respond. But 2D memory operating at picosecond speeds, AI training times could collapse from weeks to days, maybe hours. Inference becomes essentially instantaneous. The cost of running AI models drops by orders of magnitude. Energy consumption plummets. The entire AI race just changed, and China just got the key. Now, you might be thinking, this is amazing technology, but it'll take decades to commercialize, right? That's what usually happens with breakthrough materials. Graphene A was discovered in 2004. 20 years later, we still don't have graphene computers, but the Fudan team has a different timeline, and it's shockingly fast. Here's what Liu Chunsen, the lead researcher, said in the Nature paper. It took about 24 years from the first prototype semiconductor transistor to the first CPU. However, by integrating emerging technologies into the existing CMOS platform, the process in our research is significantly compressed. Let me translate that. When transistors were invented in 1947, it took until the 1970s to build the first microprocessor. 24 years, an entire generation. But the Fudan team isn't starting from scratch. They're not trying to replace the entire silicon industry. They're integrating with it. The CY01 chip uses standard 0.13 micrometer CMOS silicon as its foundation. That's mature, proven, cheap technology. The 2D memory layer sits on top, adding the breakthrough performance without requiring a complete industry overhaul. This is the key to rapid commercialization. You don't need to build entirely new fabrication plants from the ground up. You don't need to retrain an entire industry. You adapt existing infrastructure, add the 2D integration step, and suddenly you have next-generation memory. According to the research team, they're targeting a pilot production line within 3 to 5 years. Not 30 years, not even 10 years, 3 to 5 years. By 2027 to 2029, we could see commercial products using this technology. That's shockingly soon. And here's why that timeline is credible. The Fudan team has already demonstrated 94% yield. That's the hardest part of commercialization, proving the process is reliable and scalable. They've published not one, but 2 papers in Nature in the same year, showing both the device physics breakthrough and the system integration breakthrough. They've completed tape-out, meaning they've successfully manufactured the chip using real fabrication processes. And they have massive backing from the Chinese government. This research was funded by China's National Key Research and Development Program, the National Natural Science Foundation, the Shanghai Pilot Program for Basic Research. This isn't just a university research project. This is a national priority. And that brings us to the part of the story almost nobody is connecting. This breakthrough isn't happening in a vacuum. It's happening in the middle of the most intense technological competition of the 21st century. For the past 3 years, the United States has been waging an economic war to slow China's semiconductor development. October 2022 banned the export of advanced AI chips to China. January 2023 banned the export of EUV lithography machines. October 2023 expand controls to include high-end DUV equipment, chip-making materials, advanced packaging technology. The strategy was elegant. If China can't access the tools to make cutting-edge chips, they can't compete in AI quantum computing, advanced military systems. And for logic processors, CPUs and GPUs, it was working. Huawei's Kirin chips hit a wall. SMIC struggled to move beyond 7nm production. Chinese AI companies started hoarding NVIDIA GPUs before the ban took effect. The assumption in Washington was simple. This chokehold would last for years, maybe a decade. But there was a blind spot. Everyone was obsessed with logic chips, the processors that do calculations. Nobody was watching memory with the same intensity. And that's the vulnerability China just exploited. Because 2D material memory uses a fundamentally different manufacturing process than cutting-edge logic processes. You don't need nanometer precision extreme ultraviolet lithography. You don't need to cram billions of transistors into a fingernail-sized die using the most advanced photolithography equipment ever created. Instead, you grow 2D materials layer by layer using chemical vapor deposition, equipment China already has. Equipment that isn't even on the export control lists because it's considered relatively basic by semiconductor standards. The precision comes from the atomic structure of the materials themselves, not from the lithography equipment. This is asymmetric technological warfare. China isn't trying to beat the West at their own game. They're not trying to build better NAND chips using Western methods. They're making NAND potentially obsolete, using a completely different technological path that bypasses Western choke points entirely. Professor Zhou Peng, one of the lead researchers, put it bluntly. This represents a source technology that could allow China to take the lead. Not catch up, take the lead. This is what strategists call a lane change maneuver. If you can't win the race on the current track, you build a new track, while the West perfects 3D NAND silicon, reaching higher and higher with diminishing returns. China is pioneering the next materials revolution, and if they can scale this to mass production in 3 to 5 years, the global semiconductor balance of power just shifted. Now, before you think this is all about geopolitics and tech wars, let's talk about what this means for you. Because if this technology delivers on its promise, your next phone, your next laptop, your next gaming console, everything changes. Imagine a laptop that boots up instantly, every time. Not 5 seconds, not even 1 second. The moment you open the lid, it's on. Transferring a full 8K movie? A fraction of a second. Apps open the instant you tap them. No loading screens, no spinning wheels, no waiting. And here's the kicker. Because the 2D layer is so energy efficient, this leap in performance doesn't kill your battery. In fact, devices could be both dramatically faster and last significantly longer on a charge. Current flash memory wastes enormous amounts of energy. Heat dissipation is a huge problem in modern devices. 2D memory operating at picojoule energy levels? That problem largely disappears. Your phone stays cool, your laptop runs silent. Battery life potentially doubles. But the real revolution is in artificial intelligence. Right now, running powerful AI models on your device is basically impossible. The models are too big, the memory is too slow, the power consumption is too high. That's why your phone sends most AI tasks to the cloud. Siri, Google Assistant. They're not really running on your device, they're running on massive server farms. But with memory that operates at picosecond speeds, with energy consumption that's orders of magnitude lower, suddenly, running GPT-level AI models on your phone becomes feasible. Private, instant, no internet connection required. Your personal AI assistant that actually runs locally, that knows your preferences, that never sends your data to the cloud. This is the future these chips unlock. Not 10 years from now, 3 to 5 years from now. So, what's the Western response? Right now, scrambling. Behind closed doors. Samsung, Micron, SK Hynix, Intel's memory division, they're all racing to assess their own 2D materials research timelines. The brutal reality? They're years behind on 2D material commercialization. These companies spent 3 decades and hundreds of billions of dollars perfecting NAND flash. Their factories, their manufacturing processes, their quality control systems, their business models. Everything is optimized for silicon-based 3D NAND production. Pivoting to 2D materials means potentially throwing much of that away and starting over. It means retooling fabs that cost $20 billion each. It means retraining engineers. It means rebuilding supply chains. It means convincing customers to validate and certify entirely new memory technology in their products. Can they do it? Technically, yes. The science is now published. Will they do it in time? That's the $70 billion question. Because while Western executives debate in boardrooms, run financial models, calculate return on investment timelines, China's research teams are moving toward production. So here's where we stand. As we close out 2025, Fudan University publishes the world's first fully functional 2D flash memory chip in Nature. 94% yield, 20 nanosecond programming speed, production-ready technology. The same team demonstrated 400 picosecond programming speed, the fastest semiconductor charge storage ever recorded. The timeline to pilot production? 3 to 5 years. This isn't just a new chip. This is a new blueprint for the future of memory. A technical solution to silicon's physical limits. A commercial answer to AI's explosive data demands. And a geopolitical strategy to redefine the global chip landscape. The transition from lab to mass production will still take time. There will be engineering challenges, manufacturing hurdles, economic uncertainties. But the path is now clear. The proof of concept is complete. The yields are production ready. For 40 years, silicon has been the foundation of the digital revolution. But every revolution eventually gives way to the next. And the next revolution may be written not just on silicon, but on materials a single atom thick. The world is watching, the clock is ticking, and the memory of the future is already here. What do you think is the most exciting possibility for a world with memory that operates at the speed of light? Instant AI on every device? Laptops that never lag? Or something we haven't even imagined yet? Drop your thoughts in the comments. And if you want more deep dives into the technology that's reshaping our world, hit subscribe. Because this is just the beginning.